These are examples for section 12.4, secants, tangents, arcs, and segments. Example 1. Use the angle inside the circle theorem to write the equation for the provided diagram using its named points. Here we have a circle and two secants that intersect inside the circle, but not at the center. Notice that the angle in question is angle 1, or angle AED. To write an equation using the angle inside the circle theorem, we start off with the measure of the angle in question, AED. And according to the theorem, it's 1/2 times the sum of the measures of the two intercepted arcs, AD and BC. So 1/2 times the measure of arc AD plus the measure of arc BC. This is an equation that would help us solve any problem dealing with these angles and arcs. Example 2. What is the value of the variable x in the diagram at the right? Here we have a circle and we have two chords intersecting the circle inside the circle, and we have an angle. One of the angles is 68 degrees. We're asked to find the measure of x degrees here, which is one of the arcs, MN. So since we don't have a letter for this point, we go directly in for substitution. So we start with the angle itself, 68 degrees equals 1/2 the sum of the measures of the two intersected arcs. The measure of arc MN is x degrees plus the measure of arc PQ, which is 90 degrees. Now with this equation, we solve for x. Start off by using the distributive property. 68 degrees is equal to 1/2 times x is 1/2 x plus 1/2 times 90. 2 goes into 2 once, 2 goes into 90 45 times. So we have 68 equals 1/2 x plus 45. Now we have a two-step equation. We subtract 45 from both sides next. When we subtract 45 from both sides, we get 23 equals 1/2 x. To eliminate the 1/2 multiplied with the x, we multiply both sides by the reciprocal of 1/2, 2. Multiply both sides by 2. On the right side, the 2's divide out and we get x. On the left side, 2 times 23 is 46 degrees. So x degrees is 46 degrees. We found the measure of that arc. Example 3. What is the value of the variable z in the diagram at the right? Here's z. Z is representing arc, the measure of arc FG right here. We have arc, the measure of arc DF, which is 95 degrees, and we have angle E, which is 20 degrees. First, notice that this is a secant, DE, and FE is a tangent at point of tangent CF. So, according to the angle outside the circle theorem, and it would be the case that involves both the tangent and the secant. So the secant-tangent case, we have the measure of angle E, the angle outside the circle, equals 1/2 times the difference of the measures of the two arcs that are intercepted. So we have the measure of arc DF minus the measure of arc FG. Remember that when you're subtracting arcs in these theorem cases, that you always start with the arc furthest away from the angle. Here's our equation. Now we substitute in our values. Angle E's measures 20 degrees equals 1/2 times the measure of arc DF is 95 degrees minus The measure of arc FG is z degrees. Now we have an equation. We use the distributive property to get rid of the parentheses. We have 20 equals 1/2 times 95 minus 1/2 times z, or 1/2 z. 1/2 times 95 is 1 times 95 over 2 times 1. So we have 20 equals 95 halves minus 1/2 z. Since we have more than one fraction in the equation, we can always get rid of a fraction by multiplying the entire equation, or both sides of the equation, or every term by that denominator. So we multiply the right side by 2, and we multiply the left side by 2. On the right side, when we multiply both these terms by 2, the 2's divide out for this term, and the 2's divide out for this term. On the left side, we have 40. So now we have 95 instead of 95 halves minus 1z, or just z degrees. Now we need to subtract 95 from both sides in solving for z. When we subtract 95 from both sides, we get negative 55 on the left side, and we still have negative z on the right side. To get rid of the negative on the z, we can either multiply or divide by -1 on both sides of the equation. Negative divided by negative is positive, so z degrees is 55, positive 55 degrees. So z here is 55 degrees, the measure of arc FG. Example 4. A satellite in a geostationary orbit above Earth's equator has a viewing angle of Earth's form by two tangents to the equator. Here are the two tangents and the equator. The viewing angle is about 17.5 degrees, right here, from the satellite. We're going to call the satellite point S. What is the measure of the arc of the Earth that is viewed from the satellite? So from the satellite, you can see from point A, or tangent point A, to tangent point B. And they're asking, what is the measure of this arc from the satellite? So to begin with, we have two tangents to a circle, and the angles outside the circle. So by the angle outside circle theorem, the two tangents case. Let's let x, some variable x, be what we're looking for. That would be the measure of arc AB, x degrees. So using the theorem, remember it's the measure of this angle is equal to half the difference between the two arcs that were created by these 2 points. So that would be the measure of angle S, which is from the satellite, equals 1/2 times the measure of arc AEB, the bigger arc here, minus the measure of arc AB, the one we're looking for that we called X. This is the equation we can use. Now we substitute in all variables and numbers that we have. So the measure of angle S was 17.5 degrees, equals 1/2 times this right here, the measure of arc AEB, this major arc, we need to find in terms of x. Since this is x degrees, the rest of the circle, this arc right here would be 360 degrees minus this arc right here, which is x degrees. So this arc, the measure of arc AEB, is 360 degrees minus x degrees, minus the measure of arc AB, which we called x degrees. Now that we have this equation, we need to bit by bit solve for x. First of all, notice that inside the brackets we have minus x minus x. So this is 17.5 equals 1/2 times 360 minus 1x is minus 2x. At this point, we use the distributive property with the 1/2. 17.5 equals 1/2 times 360 minus 1/2 times 2x. We get 17.5 equals 2 goes into 2 once, 2 goes into 360 180 times. So we get 180 minus 1/2 times 2. The 2's divide out, and we get 1x over 1, or simply x. At this point, we need to subtract 180 from both sides, and when we do that, on the left, 17.5 minus 180 is negative 162.5. We still have negative x on the right side. Finally, to get rid of the negative 1 on the x, we can divide by negative 1 on both sides. So negative divided by negative is positive in both cases, and we get positive 162.5 degrees for the value of x's arc right here. So the viewing angle from this 17.5 degree satellite is of the Earth about 162.5 degrees right here. Example 5. Find the value of the variable in circle n. Here's circle n, and we have a secant here and a secant here that both meet at point J. From your notes, we discussed what was called the circle segments theorem, and it had 3 different cases, all a little bit different. The case that is involved here is the case with 2 secants. So, in solving this problem to set up an equation, we start with, this is L, we start with by the circle segments theorem, and the case is the 2 secants case. This theorem says that this outer part of the secant, JK, times the sum of the same one and the one inside, JK plus KL, equals the same thing with this one, the outside of the secant, JP, times the sum of JP plus PM. Taking this equation, we substitute in all variables and numerical values. JK is 6 times JK again is 6 plus KL is 8 equals JP is 7 times JP again is 7 plus PM, which is Y. To solve this equation, on the left side, we can use the distributive property, or since everything is in a number, we can go ahead and use the order of operations. So this would be 6 times 6 plus 8 is 14, equals, on the right side we do have to use the distributive property because we have a variable. 7 times 7 is 49, plus 7 times y is 7y. Simplifying further, 6 times 14 is 84, equals 49 plus 7y. Now we have a 2-step equation. We subtract 49 from both sides, and on the left side we get 35. On the right side, 7y. Divide both sides by 7, and y is equal to 5. The value of the variable y in this circle, this chord right here, is 5. Example 6. Find the value of the variable in circle n in simplified radical form and rounded to the nearest tenth place. Here we have circle n, and we have a tangent right here, and we have a secant right here that meet at one point. According to by the circle segment theorem, the secant and tangent case. We have a tangent and a secant. It says that you take the secant and do a lot like what we did in example 5. You take the outer part of it times the sum of that same outer part plus the inner part. So this would be 8 plus the inner part 16 equals RQ, or this right here, Z squared. We square the tangent. At this point, we can go ahead and simplify on the left side. We have 8 times 8 plus 16 is 24 equals Z squared. 8 times 24 is 192 equals Z squared. To find out what Z is, we need to get rid of the square by taking the square root of both sides. The square root of Z squared is Z. That's what we were looking for. And the square root of 192 will factor into 64 times 3. 64 is a perfect square factor. The square root of 64 is 8 times what's left under the radical root 3. So Z is exactly 8 times the square root of 3 units long. Approximating this, the square root of 192, Z is approximately, rounded to the nearest tenths, 13.9 units long. Example 7. The radius of circle B is 9 units, right here. This is also the radius right here, 9. Notice that from D to C is X. ED is 4 and DF is 8. Now, this circle has 2 chords that intersect inside the circle. So going back to the angle inside the circle theorem, which said that we can multiply each segment in one chord together like this. ED times DF equals AD, not AB, but AD, because that goes all the way up to the intersection of the 2 chords, times DC. Now, substituting in our values, before we do that, take a look at AD. AD, this part right here, is a combination of AB plus BD. So let's split this up, rewrite it. AD is really the addition of 2 segments, AB plus BD. So the rest of the equation, like this. Now that we have this split apart, let's go ahead and substitute in what we know. ED is 4 times DF, which is 8, equals AB, which is 9, the radius, plus BD. To figure out what BD is, notice that the radius 9 is from B to C, and from D to C is X. So if we want to find this length right here, it would be the whole thing 9 minus this part right here, X. So 9 minus X is the length of BD. So BD is 9 minus X. Close off that bracket for this, times DC, which is X. At this point, we simplify as much as we can. 4 times 8 is 32, equals, and then 9 plus 9 is 18, minus X, times X. Now we need to use the distributive property. We have 32 equals 18x minus x times x is x squared. Since we have a quadratic with an x squared term that will not go away and an x term, we need to get everything set equal to 0. Since the x term is negative on the right side, let's go ahead and add x squared on both sides so we can get it to be positive over on the left side. At the same time, we can go ahead and subtract 18x to get rid of it from over here and subtract 18x over here. And when we do that, putting it in ax squared plus bx plus c order, we have x squared minus 18x plus 32 equals 0. Now we have our quadratic in the form we need it. We look for factors. Two factors. X squared factors into x times x in the first places. Then we take c, or the third term, and we look for factors of 32. There's 1 times 32. There's 2 times 16. And there's 4 times 8. We need to be able to add those two factors together to give us 18, negative 18. 2 and 16 can be added to give us 18. So we use 2 and 16. Since the product is positive, both signs have to be the same. Since the sum is negative, both have to be negative. This is negative 2x inside terms. Outside terms, we have negative 16x. Negative 2x minus 16x is negative 18x. So these are the two factors. At this point, we set each factor equal to 0 and solve for x for both. When we add x2 to both sides, we get x equals 2 here. When we add 16 to both sides, we get x equals 16 here. Now they're both positive. We go back to our diagram. The radius of this circle was 9. Notice that x is from C to D, which is definitely shorter than 9. 9 is the radius. Therefore, 16 could not possibly be the length of x, since 9 is the radius. It's too small. And so this is too large. However, 2 will work for x, because 2 plus 7 would be 9. So x equals 2 is the answer to the variable.